LangGraph stateful message management is implemented through a StateGraph that orchestrates node communication via shared state, with reducers like add messages handling message aggregation. This pattern enables controlled state transitions, where each node processes the state and returns partial updates. We'll examine how a minimal graph is constructed by defining a state schema, adding a single node with a lambda function, and configuring entry and finish points before compilation. The invocation will demonstrate how the state evolves through the graph, producing a structured message output.
From typing, import annotated. From typing extensions, import type dict. From LangGraph, graph import StateGraph. Class state type dict. Messages, annotated list add messages. Builder equals StateGraph state. Builder add node chatbot lambda state. Messages, assistant hello. Builder set entry point chatbot. Builder set finish point chatbot. Graph equals builder compile. Graph invoke. Hash messages. AI message content equals hello. ID equals.
This example demonstrates a minimal StateGraph implementation for stateful message management in LangChain. The pattern uses a builder to construct a graph where nodes communicate through shared state, with the messages key annotated to use the add messages reducer for merging message lists. The graph consists of a single chatbot node that appends a greeting message to the state, configured as both the entry and finish point. The mechanism shows how StateGraph enables declarative workflow construction, where nodes transform state and reducers handle aggregation. Here, add messages ensures message lists are properly merged when multiple nodes contribute to the same state key. The builder pattern provides a clean API for graph construction, with compile producing an executable graph that implements the runnable interface. This approach is useful for workflows requiring shared state between components, offering a structured alternative to manual state passing. The trade-off is added complexity for simple cases, though it scales well for multi-node workflows. The example highlights the framework's design for composability, where nodes focus on state transformations while the graph manages control flow and state aggregation. Let's break it down.
From typing, import annotated.
Imports annotated from the typing module, which enables adding metadata to type hints through annotations.
From typing extensions, import type dict.
Imports typed dict from typing extensions for creating dictionary types with type annotations.
From LangGraph, graph import StateGraph.
Imports the StateGraph class from the LangGraph graph module, which provides a builder for creating state-based graphs where nodes communicate through shared state.
Class state type dict.
Defines a state class that inherits from typed dict, creating a type-hinted dictionary structure for representing application state in LangGraph. This establishes a strongly typed schema for the shared state that nodes in a StateGraph will read from and write to, though the specific fields aren't visible in this single line. The typed dict base ensures type safety when accessing state keys while maintaining dictionary-like behavior.
Builder equals StateGraph state.
Creates a StateGraph instance using the state class as its state type. This initializes a graph builder where nodes will communicate through a shared state of type state. The builder is not yet executable and requires additional configuration before compilation.
Builder add node chatbot lambda state. Messages, assistant hello.
Adds a node named chatbot to the StateGraph that takes the current state and returns a new state with a single message from the assistant saying hello. The lambda function defines the node's behavior, which in this case simply appends a greeting message to the messages list in the state.
Builder set entry point chatbot.
sets the chatbot node as the entry point for the state graph, meaning it will be the first node executed when the graph runs. This is equivalent to creating an edge from the special start node to the chatbot node.
Builder, set finish point chatbot.
Marks the chatbot node as a finish point in the state graph, causing graph execution to terminate when this node is reached.
Graph equals builder compile.
Compiles the StateGraph builder into an executable graph object. The resulting compiled graph implements the runnable interface, enabling methods like invoke, stream, and a stream to be called on it. This is the final step in transforming the graph definition into a runnable workflow.
Graph invoke.
Invokes the compiled graph with an empty input dictionary, triggering executions starting from the entry point node and processing through the graph until reaching a finish point or completing all possible paths. The empty dictionary serves as the initial state for the graph execution. This minimal state graph implementation demonstrates LangGraph's declarative approach to stateful workflows. The pattern centers around a strongly typed state schema using typed dict, where the messages key is annotated with the addMessages reducer for proper list merging. The builder pattern provides a clean API for graph construction nodes, are added with simple state transformation functions, entry and finish points define the execution flow, and compile produces a runnable graph. The single chatbot node shows how nodes focus solely on state transformations, while the framework handles control flow and state aggregation. This design scales well for multi-node workflows, but introduces some overhead for simple cases, trading direct state passing for structured composability. The key insight is how the reducer annotation on the state schema enables automatic message list merging, allowing nodes to contribute to shared state keys without manual coordination.
The state graph compiles itself into a finish point that never arrives. Each node a message that refuses to be sent.